Today, we're going to take a look at rolling contact joints. I've been working on a robotics project, and just due to the size of the features, it's hard to get mechanical ball bearings in here. And so I decided to use rolling contact joints. And this project's going to be stalled for a little while just because I've got other things to work on. But I decided to make a quick video about the joints in particular because they're really interesting and I don't think a lot of people know about them. So I want to introduce this joint to folks for whatever project you might be working on. A quick overview is that I'm trying to build an avian or bird-inspired robot. Basically, it'll hop around and look like a bird. This was my first attempt, and it uses traditional ball bearings and carbon fiber rods for structural support, as well as the shafts going through the bearings. And these aren't the smallest bearing that you can find, but they are getting close to the smallest. There's kind of just a lower limit as to how small of bearings you can get. And that puts some design limitations just based on kind of feature sizes around the outer diameter and inner diameter of these bearings. So I wasn't overly happy with this design for a lot of reasons, but especially for the bearings. So I started working on a new design, which uses these rolling contact joints. Because the design I'm working on is so small, I decided to print out a scaled version so that we could look at the mechanism a little easier. Okay, so a rolling compliant rolling contact joint is made up of two halves that have some kind of curved surface. And the curved surface on both sides roll against each other. That's basically it. There's not much more to it than that, but there's a lot of nuance into the types of surfaces you build here and also how you connect the two halves together. So this particular joint is designed to rotate in this manner, and there are two main surfaces that we care about. There's this rotational surface on this half and the inside section over here. These two outer walls are just to help provide some rigidity to prevent kind of out of plane movement in this direction, but it's not really the part we're interested in. We care about these two faces that mate and rotate together. So on this side, we've got a flat section that transitions into a gentle curve and then a steeper curve on the backside before turning into another flat. And then I'll show a cross-section view of CAD, but here we've got a relatively flat section followed by two steep curves on either end. And that's one of the nice things about these contact joints is that you can engineer the surfaces that are, mating together and get different behaviors depending on where they are in the travel, which is not something you can easily do with regular ball bearings. And this is basically how joints in the human body works, in mammals, in birds. You've got two sides of the joint that are rotating against each other in a nonlinear fashion, and that constrains the movements of your limbs. The other really striking feature about these joints is how they're held together, typically using a compliant mechanism, either a cable flexure or a solid band. I'm using fishing line. This is actually called Dyneema. It's a ultra high molecular weight polyethylene, I think. You can get it in very thin line, which is what I needed for these small mechanisms, but you can use metal cables or metal straps, like whatever works. And basically you have two loops, one coming on the outside going in and the inside coming out, and that holds the two halves together. You can see that in my design I have it split up into 4 individual channels, and this lets me kind of braid or sew the line through the joints and hold it together, which gives you a mechanism that rotates. So I'm going to try to show you how this is sewn on camera, but bear with me, it's kind of hard to capture it all. Hopefully it's not too confusing. But basically we're going to go through a hole in one side, up around the channel, onto the other side, and then back through a hole. And we just repeat that process, making kind of a figure 8 the whole time. So first we'll start on this side, we thread it through a hole, pull it through, wrap it around the channel, grab our other half, and thread it back through the top hole, and pull that through. And that is the basic pattern. So you can see here we've gone on the underside, and then it comes up in the gap between the two, and then goes back down into the hole to the underside. Now what we do is we go to the other side. So you go all the way across and thread it through the last hole on this side, pull that through, and we repeat the pattern. So it's from the top, now we go underneath. Through the channel, and then we want to come back up through that hole. Okay. Now we need to basically do the inverse for the inner two. So to do that, the best way I found is actually to loop it around the outside like that. You can hold on to it, and we'll want to go back through this section here. So going through the second hole on the underside, out the top, and repeat the process in reverse. Thread it back through the middle and into the middle holes on the other half. I'm going to thread this back through the middle. Okay, and now it is basically done. So we can tie it off however you want. I found just looping it through the edge here a few times is sufficient to hold it. Okay, so I tidied this up a bit off camera, but you can see that we have our completed joint now. It naturally wants to stop about this far. There's some compliance there because it's a cable, but it doesn't really want to bend much more than that because there are two kind of steep angles right next to each other, and so that prevents it from wanting to move much further. Whereas this side very easily rolls forward. Actually, it rolls a bit too far forward. This was a design flaw with my current model. It kind of gets here and then just keeps going, which is not ideal. So that's just a mistake on my part. But you can see how the forward versus back rotation motions are very different due to the inner shape of the contact joints. And then if we look closely, you can see the pattern. So I've got, on this side, it's over, under, over, and then the reverse on the top, under, over, under. You'll notice it's also pretty strong out of plane. So obviously it rotates in this direction, but we don't really want it to rotate in this direction, up and down. And there's a little bit of play there, but it's pretty robust. And that's a combination of these two outer guards help prevent it from rotating, and also just this mechanism, because it's a cable, the cable doesn't really want to stretch in a rotational direction. And so applying force like this, there's just not a lot of room for the cable to stretch and pull it in that direction. Whereas this works easily because the cable isn't stretching at all. It's just shifting where it's landing inside the trench. So it's basically zero friction this way and pretty strong in that direction. And this is just tied, those are just two little knots. So if you actually had a mechanism to hold this cable firmly in place mechanically, this would be a pretty robust joint until that happens. And then the poor guy has a dislocated joint. So you can see this joint that we built is effectively this joint here. So why choose rolling contact joints over just a traditional ball bearing? As I mentioned, size can be an important factor. Ball bearings just have a lower limit as to how small you can make them because they're relatively complicated assemblies, whereas a rolling contact joint can be made basically as small as you want. They have extremely low friction. So as you can see here, this is one of my earlier tests. Due to the nature of the two surfaces rolling on each other and being held together with some kind of compliant flexure mechanism, there's very little in the way of friction between the two halves. And honestly, they just look cool, which I think is an important part for robotics. You gotta make them look neat. Now, I didn't invent this joint at all. You can find it in tons of different robotics projects, but you don't really see it too much in amateur or hobby projects, which is why I thought, I'd make this video just to kind of spread some awareness. Because it is a neat mechanism and it lets you build, in my case, very small joints that would be otherwise pretty impractical to do with bearings. If you're watching this video before June 14th and you're on the West Coast or feel like flying out to the West Coast, you should come to OpenSauce. I'll be there. I think 150 other creators are signed up to be there and something like 500 exhibits from folks in the community. So I think it'll be a lot of fun. I really wanted to go last year, but it conflicted with something, so I just couldn't make it. But I'm excited to be there this year and see all the cool projects. I'm hoping to bring the little prototype camera sensor that I made in the last video and set it up with like a microscope or something so people can take a look at it with their own eyes. But yeah, June 14th, June 16th, hope to see you there. I'll share some more details about this project in the future once I get a little bit more done. For example, you can see there are these cables on the front and back, and those are actually unrelated to the joints. Those are the actuation mechanism, and they'll basically act like muscles that pull different parts of the structure to make it hop. But I don't have nearly enough of this done to actually share yet, so we'll just hang on to that for a future video. But otherwise, I hope this was interesting and just a nice, quick primer on a new type of robotics joint. Thanks for watching, and I'll see you next time.